Good day, everyone, and welcome to this month's webinar on Wi-Fi security in 2026. We're going to be looking at the security solutions that are available in our modern Wi-Fi networks, and we're going to talk about some of the hits and misses, some of the little idiosyncrasies of how these technologies are implemented, because you'll hear of a lot of things that are available, and what someone means by the word available can be very different depending on who's talking. So there are things that are available from the perspective of having been defined in a standard or within the WPA3 certification, but many times those defined things are optional. And that doesn't therefore necessarily mean that they are actually available in real systems. And they may not be available in real systems in such a way that they work appropriately. So here's what we find in the industry. We find that when a particular feature or capability is optional in either the 802.11 standard or Wi-Fi Alliance certifications, that feature tends to be implemented more, let's just say, haphazardly within vendor solutions than a feature that is required. Now, part of that is because required features are usually more exhaustively and intricately defined in the specifications, and optional features are often defined with a bit more vague descriptions, and the end result can be some incompatibility. So what I mean by that is sometimes with these optional features, you'll see that some clients implement them in such a way that they work, and some clients implement them in such a way that they don't work, or that they work inconsistently. So these are some of the problems that we always face when we're dealing with this required versus optional feature set in wireless technology. And then there's some confusion that often happens as well out there in the community because of phraseology. So the standard might say that something is required, or it might say support for something is required. Well, those are two very different things. To say that something is required means it must be there. To say that support for something is required simply means that the device needs to indicate that it supports it. If the standard also allows for other things to be used, a device could indicate it supports it and then use that alternate thing instead of the thing that it also supports. So all of this just introduces a lot of confusion often to what's actually going to effectively be implemented and functional on the network. And so that's a really important concept to keep in mind when dealing with this. All right, so let's jump right in. And what I'm going to do is, first of all, address the reality that within any security solution, your weakest link can be the breaking point, right? And so if we have, for example, with WPA3, if we have enabled transition mode, then what we're basically saying is that devices that don't support WPA3 can use WPA2 instead. And the reality is that that means that there's at least a partial entry point to the data traversing your network through those WPA2 devices that are still on that network. They are therefore a bit weaker than the WPA3 devices, and therefore form that better point of attack for an attacker that's trying to gain some level of access to your data. This does not necessarily mean that full access to your entire network is exposed automatically just because you're using transition mode, but it is an important thing to always consider. What are the weak links that still exist on my network? And when we're implementing security, we often think of the AAA model: authentication, authorization, and accounting. So we're asking, in relation to Wi-Fi in this case, what are we using for authentication? How are we identifying devices or users? And what are the actual protocols that we're implementing to validate those identities? So authentication is effectively the validation of a claimed identity. The claimed identity might be an identity of a user, or it might simply be the identity of this mystical entity that should be allowed access to the network. Now, what in the world do I mean by that? Well, what I mean by that is that when you're dealing with things like WPA3 SAE, WPA2 PSK, or personal, what you're doing is you're really just proving that you have the right password. You're not proving any real identity per se, but you could say that the identity is an entity that has the password and should be allowed on the network. Okay, so we're authenticating that conceptual identity in that case, not an actual identity. When we get into WPA2 Enterprise and WPA3 Enterprise, then we're looking at actually validating identities, either usernames and passwords tunneled in authentication procedures or certificates used for identity validation and so forth. So it is important to keep in mind that when we talk about authentication within the confines of Wi-Fi, we're not always talking about what we mean when we talk about authenticating users on networks or authentication in general in network systems. Then we're usually talking about validating a claimed identity with that identity being associated with a very specific real physical or virtual entity. In the case of Wi-Fi, with personal security, whether that's WPA3 or WPA2, we are really validating this virtual entity that is simply defined as a entity or an entity that should be allowed on the network because it has the right password. Okay, it's really as simple as that. We're not determining a specific device or a specific user in those cases. So authentication is about validation of identity, whether real or virtual. Authorization is about deciding what they can do. And this is done through access control lists and a lot of network systems, servers, as well as network routers and switches and things like that. But it's also about authorization by constraining the portions of the network to which they can gain access. And this comes through a combination of network architecture and then assign parameters to the authenticated entity. So for example, if we have an assigned parameter like a VLAN, a virtual local area network, that is assigned to a particular authenticated entity, then when they're on that VLAN, that might constrain what they can access, therefore limiting their authorization. So there are ways that we can bring authorization concepts into this without even going up to the user level per se within our Wi-Fi networks. And then accounting is about logging. So logging in general could simply be logging that a device associated with an AP, or that it is associated through a controller, or that it has attempted an association, or it could be more advanced where we're using overlay monitoring solutions and we're logging all of the different activities that happen, whether through an AP or controller or not. And so accounting could fall into several of those various categories. Our main focus here today is going to be over here in the authentication area, where we talk about WPA2, WPA3, what they bring to the table, and the authentication that they provide. Now, one of the key things that a lot of people miss when they look at the WPA2, which is still so widely used in our Wi-Fi networks today, is that your passphrase is not your pre-shared key. So quite often we talk about using WPA or WPA2 PSK, kind of as a synonym for WPA2 personal, right? And so a lot of people think that the passphrase is the PSK, but it's actually not. So the standard defines a pseudo-random function, the PBKDF2 function, which is a password-based key derivation function, PBKDF. And what we do is we take our passphrase and the SSID and we run it through this pseudo-random function. The parameters that are in here passphrase, okay, that's your passphrase. SSID, that's your SSID. Then the 4096, that's how many times or rounds we pass this data through the PRF, the pseudo-random function. And then the 256 is, all right, what is the output data? What are we getting out of it? Well, we're getting 256 bits out of it. And that's really what we're getting with WPA2 personal. WPA personal might need more than 256 bits because we need some special MIC keys as well. So there can be some extra values there. But with most modern networks, we're dealing with this 256-bit pre-shared key. So the pre-shared key provides the materials for the PMK. And I should say I misspoke. I kind of got ahead of myself there. We're getting a 256-bit PSK regardless, but that 256 bits may be turned into more or less bits as it eventually becomes the PTK, depending on whether we're using WPA or WPA2. So the PSK provides the materials for the pairwise master key, or we could say the PSK equals the PMK. And then that goes through the four-way handshake, which generates the PTK, the pairwise transient key, which contains the actual keys. We'll get into that a bit more later on. But for now, just know that the passphrase is not the PSK. So it's not what you start with when you go into the four-way handshake. What you start with is the passphrase. Then you generate the PSK from that. That becomes your PMK, which is fed into the four-way handshake. Now, when we're dealing with our networks today, we're looking at enterprise or personal solutions. The enterprise solutions use Radius 802.1x EAP. The personal solutions are password-based, and this is still true even with WPA3 SAE. There's still a password involved. We'll talk about the difference later, but they're still password-based. In the case of enterprise, we're taking that whole password element out, and we're actually using real authentication, is the way a lot of people like to say it. We're actually doing authentication across the network and utilizing that in order to get our PMK to do the four-way handshake. Now, again, all of this will become clearer as we get further into this, where the four-way handshake fits and so forth. So the enterprise flow then is going to be that you'll have a client device, laptop, tablet, mobile phone, barcode scanner, whatever it is, and you'll have an AP, and you'll have a Radius server on the back end. In this screen, this is defined as an authentication server, or AS. That authentication server may or may not use an external user database. Okay, so the external user database, like an LDAP directory, something like that. So we can use the LDAP protocol, Lightweight Directory Access Protocol, that's what LDAP stands for, to access some backend database. This could be literally a database. It could be a Windows domain, right, from a Microsoft environment. So whatever that data source happens to be, we use that for our actual credential management related to the authentication server or the Radius server. Now, the Radius server may just use its internal database. It may not have a backend database. In smaller deployments, you might just use an internal database. But the key here to understand is that the authenticator is the AP or controller, and it is not the Radius server. So the Radius server is the authentication server. The authenticator is the proxy, if you will, between the client device and the Radius server. So the client is known as the supplicant. The authenticator is, again, either the AP or the controller or possibly some other system, but generally the AP or controller. And then the authentication server is typically a Radius server. So this is the architecture for how enterprise solutions work. So the Radius server can provide the authentication, the authorization, and accounting. So it can do all of these parts and pieces depending on how you implement it. Now, the way all this is going to work is within the authenticator, we're implementing this protocol by the IEEE called 802.1x, and that is a capital X, not a lowercase x. You'll see some people type it with a lowercase x. That's technically inaccurate. We try to be accurate to the representation of it, but there's actually a reason for it. So there's a reason for a capital X instead of a lowercase x. Lowercase letters are used for amendments, and uppercase letters are used for self-contained specifications. So for example, 802.11ax, the ax is lowercase because it's an amendment to the 802.11 standard. 802.1 capital X is a specification within the 802.1 series all by itself. It's not an amendment per se to another specification. The same is true, for example, for 802.1q, 802.1d, and so on. So when you see a capital letter, that means we're talking about a standalone specification within the series. And when you see a lowercase letter, we're saying it's an amendment to that specification. Okay, so just a little tip for you in case you've never heard that before. So within the authenticator, we implement these things, these virtual entities known as port access entities, or PAEs. And these give us port-based access control. What? Well, the way this works is we have within our AP, within a switch, on a wired network, and so forth, these port access entities. And within an AP, obviously, you have one radio, and you might have 100 client devices that connect to it, right? So obviously, these are virtual PAEs. There's no physical switch port that each one having its own PAE. Instead, there's a virtual port access entity port within the switch. And the concept is that you have two virtual ports in here, a controlled port and an uncontrolled port. Now, this can get a bit confusing because the terms controlled and uncontrolled, I mean, you can take them in a lot of ways, right? So an uncontrolled port, you might think, oh, well, that lets anything through. And a controlled port, well, that only lets certain things through. Well, actually, the uncontrolled port is allowed for communications immediately. That's how it's uncontrolled. But the only communications it will allow are authentication communications. Okay? So it's not allowing regular data communications, just authentication. In this case, EAP communications, right? So the uncontrolled port allows access, but only for authentication. The controlled port does not allow access by default. And that's the starting point on the left side here, unauthorized. After we are authenticated with some extensible authentication protocol, then the controlled port opens and we're now allowed to send regular data communications on the network and receive them. That's the authorized state. Okay? So this is this concept of a port access entity. Controlled and uncontrolled virtual ports. In the unauthorized state, the uncontrolled port can be used in order to do authentication. The controlled port is blocked. In the authorized state, the controlled port is unblocked so that we can utilize it for normal data communications. So how does this all work together with 802.1x EAP? And remember, this stuff we're talking about here is really enterprise deployment, WPA2, WPA3 enterprise. So basically the EAP 802.1x EAP framework is simply that we're going to go through an 802.1x EAP authentication. We often call it an 802.1x EAP authentication because we're using 802.1x. That's the port authentication, port-based authentication, right? We have the PAEs. So we're using 802.1x, and to get that controlled port open, we're using EAP authentication, okay? And the basic concept then is that we go through the 802.1x authentication process, And once we have EAP success, then we have the materials that we need in order to generate our encryption keys. Now, notice the bottom of the screen here says, IEEE 802.1x controlled port blocked for station. Wait, what? But the 802.1x authentication is done. It is, but we don't have our keys yet. In order to get those keys, we need to go through a four-way handshake. And we'll get to that in a moment. Now, the two most common EAP methods that are used for typical laptops, tablets, things like that are on Wi-Fi networks are protected EAP or PEEP and EAP TLS. And those are the only ones we'll really talk about. And we're not even going to go into excruciating details of the individual steps here like we would in a CWSP course or something like that. But basically protected EAP, which is on its way out. It is deprecated by Microsoft. It's eventually going to go away, but a lot of people do still use it, even though it's been deprecated now for a couple of years. Protected EAP is a tunneled EAP method. And so what that means is that we establish a tunnel and then we use MS-CHAP v2 inside of the tunnel, or we use EAP TLS or EAP GTC or something inside of the tunnel. Usually EAP MS-CHAP v2, because the whole reason that PEEP is seen as beneficial is because we don't need client certificates, so we don't want to use EAP TLS inside the tunnel. And so we end up using EAP MS-CHAP v2 in the tunnel in most cases. So it looks like this, but again, we're not going to get into the nitty-gritty details of this. This is covered in detail in the CWSP materials, but basically you can see the general flow of this communication process that happens. And this is recorded and will be on the CWNP TV YouTube channel, so you can always pause this once it's uploaded there within the next few days in order to look over it in more detail. Now, EAP TLS is going to require client certificates in pretty much all implementations. And so the client has a certificate, the server, and that's the Radius server, has a certificate. And these certificates are used in this EAP exchange in order to authenticate both the server and the client. And once we go through this process, we have the ability to do the four-way handshake. And as you can see toward the bottom of this diagram, we see step 8 is the four-way handshake. And after that is completed, then the 802.1x controlled port is unblocked and allows general data to pass. So all of this that we're talking about is about establishing what is called a robust security network, or an RSN. Now, technically speaking, the 802.11 standard defines an RSN really as any association and authentication with an AP that ends with a four-way handshake, and a successful four-way handshake specifically, I should say. So that means that technically TKIP, or what's known as WPA, still falls into the category of an RSN. Okay, so an RSN is, by definition, not necessarily something you would want to use on your modern network. Not all RSNs are created equal. You don't want to use WPA unless you're absolutely forced to for some reason. Then you might want to think about it. So this phrase on this screen that says TKIP, CCMP, and GCMP are minimum ciphers, well, it means minimum to be called an RSN. That does not necessarily mean that it is the minimum you should be using on your network. All right. Generally speaking, you want to use CCMP or GCMP. These are the more modern ciphers. So a robust security network is a network where all associations are robust security network associations, or RSNAs. In other words, all of the associations to that BSS are using TKIP, CCMP, or GCMP. Now, these phrases, TKIP, CCMP, GCMP, they're hard to even say sometimes. These are just the acronyms for cipher suites, okay? So TKIP is the Temporal Key Integrity Protocol. CCMP is, well, a whole bunch of things. basically, it's a very long spelled out acronym because the C stands for one thing, and then the CMP stands for, it's just long. You don't have to know it for certification exams or for the real world in any way. But know that as you move from left to right, you're going from older to newer, at least in the way they've been implemented in Wi-Fi. So TKIP was the older stuff available to us as we transitioned from WEP to CCMP, and then CCMP, of course, was available, and then eventually GCMP became available, and so forth, right? And you'll see these come up again a little later as we talk about some of the newest security solutions that we have today. Within your wireless communications, there is an RSN element. So the RSN element, which used to be called an RSN information element, but nowadays in the standard, they've taken the information part out and they just call it an RSNE instead of an RSNIE. So they do change things like that every now and then in the standard specifications. But basically, this element defines what suite am I using. So for example, am I using CCMP? Am I using GCMP? Am I using TKIP? What suite am I using for my group and for my pairwise keys? So the difference between group and pairwise is a key used between a pair. So it's unicast, one end to another end. Those two ends are using this. That pair of endpoints are using it. It's a pairwise key. A group key is used for many devices that are in a group. So if you have a group message on a BSS, that can be encrypted with a group key. But a message going from one station directly to the AP or from the AP directly to one station is going to use the pairwise key, okay? So pairwise, it's just between a pair. I don't know why they didn't call it pairwise and groupwise. Don't know why we don't think the group key is very wise, but the pair key is wise. Not sure on that. That's meant to be a joke, by the way, but Tom's humor is not always easily detectable. So the RSNE is going to tell you the group cipher suite, the unicast cipher suite, the authentication and key management suite, or AKM suite, and so forth. So these are simply going to let you know what are being used in these different solutions. And the codes that you'll see are things like the cipher suite. Well, if it's 1, you're really in trouble because you're using WEP. If it's 2, you're in a bit of trouble because it's TKIP. If it's 4, you're probably okay if you're modernly patched. You're using CCMP. If it's 5, you're in trouble again. You're using WEP 104. If it's 9, you're using GCMP 256, so you're probably okay there. Again, all of this probably okay stuff depends on, are you properly patched, right? Just this month, there's a new vulnerability that's been reported within the, if our memory serves right, it was the Broadcom chipset that has some vulnerabilities in there that expose networks to certain attacks and issues. But there's a patch available, and vendors that use the chipset are either already have or are releasing patches to fix that. So just because we're using good cipher suites does not mean those cipher suites have been implemented goodly. In other words, the programmers have to implement it right. And if the programmers do something wrong in the implementation, it can make it vulnerable to an attack, right? That does not mean that GCMP 256 itself is necessarily vulnerable, or even CCMP with AES 128 is itself inherently vulnerable. It just means that the way it was implemented was vulnerable, and now we need to patch it to fix that implementation problem. So this is really, really important to keep up with. You always have to make sure you're staying patched. It's not just about which of these suites am I using. And then you have the authentication and key management suite. So the difference between these, cipher suite, what am I using for my encryption and for my integrity and so forth in my communications, right? That's what that's telling me. The AKM suite, how am I getting that? How am I getting the keys that I use for the encryption? Am I using 802.1x? So I'm going through PEEP or EEP TLS to get my eventual PTK after the four-way handshake. What is the flow that I'm using to get to that end result? Or am I using PSK with WPA2? Or am I using SAE with WPA3? Okay, this is the question that we're getting answered by the cipher suite type and the AKM suite list. This is one of the reasons protocol analysis can be important. So what you're seeing right here is a screen capture of a protocol decode in a protocol analyzer. So you can do this as an audit of your network and you can see what's being used out there. Okay, and that's exactly what's happening here. So all right, you ready for this? What this gives us then, through all this process, is ultimately what we call a key hierarchy. We get keys from keys. Now, technically speaking, it's only a key if you actually use it to unlock something, right? So I guess we could argue that the MSK is a key because we use it to unlock the PMK, and the PMK is a key because we use it to unlock the PTK. I prefer to think of keys as what are actually used in encryption. I think that makes it easier for most people. Technically, within the science of cryptology, there's the concept of the derivation of keys and multiple layers of derivation, and it is considered a key source that is used to derive another key. And so we can technically still call it a key, but the reality is that we don't just have an encryption key. And you'll even hear people say things like, well, your PTK is your encryption key that you use to encrypt your data. That's not technically true. So let's see this hierarchy here. We start with the master session key, the MSK at the top. This comes out of 802.1x EEP. If we're using that. Now remember, if we're not using 802.1x EEP, then we have the pre-shared key, we pass it through the password key derivation function, right? And we get our PSK from that, and then effectively the PSK becomes our PMK. So we get to the PMK level either by deriving it from the MSK or deriving it from the PSK. One of those two, okay? Now, once we have the PMK, then we go through our four-way handshake to get our PTK. Ignore the left side, the group stuff, just ignore that for now, okay? Once we have our PTK, then we have all of the keys that we need for our communications. And there are 3 that are required in all Wi-Fi deployments. And there may be others required depending on what you're doing. So if you're using WPA with TKIP, then you need those temporal MIC keys that are mentioned down there. You only need those with TKIP, though. You don't need them with CCMP. You don't need them with GCMP. They're only used with that. In all cases, we have a key encryption key, a key confirmation key, and a temporal encryption key, which is sometimes written as a TEK and sometimes just as a TK, depending on how people decide to acronymize it. So it is definitely varying across different literature and documents. The key is to know, no pun intended, that the TK or TEK, that is your encryption key. The key encryption key, well, that's used to encrypt the group key during the four-way handshake. The key confirmation key, well, that's used for integrity management during the four-way handshake. Okay. And so those are used for different things. But what are they? How does this work? PTK, you got all these keys. Well, it works like this. So your pairwise transient key is going to be some number of bits long, right? Now I say some number because if you're using secure wake up radio, which is a newer part of the standard that nobody's implementing yet. But if eventually down the road we're using that, we're going to have extra keys that are part of the PTK for that. Again, if you're using WPA, TKIP, then you're going to have the MIC keys that are extra keys. And when I say extra keys, so notice the highest bit value that you have here is the TK going up to bit 383, which that's the 384th bit, because remember we start at 0. So bit 383 is the 384th bit. So bit 384 and up would be your WSUR keys. It would be your MIC keys and so forth if you need them. So the way it works is simple. You get all these bits generated, and bits 0 to 127 are the key confirmation key. Bits 128 to 255 are the KEK, the key encryption key, and bits 256 to 383 are the TK. So those are your bits that you're using. Now, this is assuming, obviously, that we're using 128-bit TK. We may need to do some extra processing if we're using 256-bit GCMP. But this gets you started, and you're thinking for how all of this flows together. Now, where does this PTK come from? It comes out of the four-way handshake. So basically, the four-way handshake, remember, this happens after 802.1x EAP, or it starts immediately if we're using pre-shared key. Or if you're using WPA3, it happens after the SAE Dragonfly handshake. So depending on what you're using for your AKM, are you using SAE? You're going to do Dragonfly and then this. You're going to do the SAE handshake and then this. If you're using 802.1x, you're going to use the 802.1x EAP authentication and then this. If you're using WPA2 PSK, well, you just start with the PSK and then this. Okay, so what you do before the four-way handshake is what changes with the various AKMs, authentication and key management suites you might be using. And then basically you're going to go through this four-way handshake. Now the four-way handshake is called that because there are 4 messages. Message 1, 2, 3, and 4. And the first 2 messages are used for the supplicant and authenticator to exchange their nonces. Number used once, that's a nonce. So they're sending this back and forth. And once both of them have those nonces, they can use that in the mathematical algorithm to derive the proper PTKs. And then in message 3, the authenticator now assumes the supplicant has the proper PTK, so it encrypts the GTK. Remember that key encryption key part of it? It encrypts the GTK and sends that down in message 3. Then the supplicant can decrypt the GTK, and upon successfully doing so, it knows it has the proper PTK. So it says to the authenticator, we're good to go. That's message 4. Message 4 is good to go. All right. So message 1 and 2 is let's go, and here's my number I'm going to use. Message 3 is all right, based on those numbers we exchanged, here's the GTK encrypted with what you should be able to decrypt. The client decrypts that and says, I decrypted it successfully. Awesome. We're good to go. And that's message 4. And that's effectively what the four-way handshake is about. Now, here are your technical details of that handshake, broken down with all of the different intricate element parts of it. And so basically all of these are bit values that are sent. So the first bit in the handshake message is going to be the initial key exchange complete, yes or no. So that's obviously set to 0 in message 1. The second bit is the MIC included. That's going to be 0 in message 1 because we don't have the PTK derived yet to be able to calculate those. Response required, that's set to 1 because obviously we can't be done after message 1 when we're supposed to have 4 messages. Install is set to 0 because after just one message, there's not enough knowledge to install it. This says P, key type P for pairwise. Well, it's actually a bit value, but we say P because that's what it always is in these messages. We're using it to generate a pairwise transient key. The next bit is reserved. And then we have the key receive sequence counter, and that's set to 0 in the case for the GTK that's being installed. We haven't got up to the GTK yet, so not talking about it. So we're just leaving it at 0. Then we have our A nonce, which is not just 1 bit. It's the actual number, but it is bits. Everything's bits, right? When you send something on a network, it's all 1s and 0s, but those 1s and 0s represent a number. And then, of course, the MIC is not included, so that field is simply set to 0. And then here's how the message evolves as it goes through the exchange process. So you can see that the first bit stays at 0 in message 1, but it becomes 1 in message 3. Well, what was that first bit? The first bit is this the initial exchange complete? In message 3, from the authenticator's perspective, yeah, everything's been communicated, right? So it's now set to 1. And I'm not going to break all of these apart in detail. Again, this will be recorded, placed on YouTube. If you want to pause, reflect back and forth between the previous breakdown slide and this one, you'll be able to see how all of these break apart and form the 4-way handshake in excruciating detail. So what we do now with WPA3 is we modernize our security methods and we say, let's start using even better stuff than we've used before. And so you can see that we have 2 things really, WPA3 and OWE. So WPA3 is the new certification from the Wi-Fi Alliance, came out several years ago now. We're talking about 7 or 8 years ago. But keep in mind that WPA3 is new again, and then it's new again, and then it's new again. This is important to keep in mind. So WPA3 today does not look at all the same as it did, say, in 2019. It gets updated. And anything that is certified today has to meet today's requirements. And those updates to WPA3 are usually done in order to fix vulnerabilities that are discovered or to enhance requirements and constraints and so forth. And so WPA3 can be either, again, personal, SAE, or enterprise. And the only difference is that personal uses a passphrase, and then it uses that SAE, simultaneous authentication of equals, that dragonfly handshake, to go from the passphrase to the PSK. Well, not the PSK, but the PMK rather. And then WPA3 Enterprise uses 802.1x EAP to generate that MSK, which we use to get our PMK, to again start the 4-way handshake, remember? And then opportunistic wireless encryption is really just that, I call it the duh moment in Wi-Fi. So we have the reality that we've used something like this for security on the web for a long time. You might call it opportunistic web encryption on the web. In other words, it's what we call HTTPS, right? And HTTPS says, well, we don't really need any client credentials, but we can still generate keys and encrypt the communications. And that's done on the web and has been for decades. So they said, why wouldn't we use something like this in order to have encryption on Wi-Fi networks? So we'll just do a Diffie-Hellman type exchange between the AP and the client and generate encryption keys to use to encrypt that session. So that's basically OWE. And it has been implemented in Wi-Fi certifications, and many more and more devices are coming out with support for it as time goes on. So WPA3, of course, is the 3rd version of WPA. It was created just after the crack vulnerability. A lot of people say it was created in order to protect against crack, but it was really kind of being developed already. And it's just that the timing ended up that crack is announced and like the next month, WPA3 is here. So WPA3, of course, helped to protect against it. But then, of course, later vulnerabilities are discovered in WPA3 and we have to patch against those as well. That's just the reality of how all security works. Implementations eventually have vulnerabilities discovered in them and we fix those vulnerabilities. But it's important to know that WPA3 is required in Wi-Fi 6 in 6 gigahertz. So if you're using 6 gigahertz, and this is still true with Wi-Fi 7, then you've got to use WPA3. There is this transition mode that allows you to have WPA3 but fall back to WPA2. We'll talk about some issues with that in a moment. It does also require mandatory use of protected management frames, or 802.11w, within the use of WPA3. So basically what WPA3 does is it adds this SAE handshake before the four-way handshake. So instead of just starting with a passphrase and using an algorithm that is known to generate the PSK from that, and then doing the four-way handshake, we instead use the passphrase through this SAE handshake that's based on elliptic curve cryptography and so forth to generate the PSK or the PMK to start into the four-way handshake. And what that does is it makes it so we have what's called perfect forward secrecy, because basically breaking something today doesn't break everything in the past, because every time we go through that SAE handshake, we're generating different results, even though we start with the same passphrase. Okay, so that is a simplification of the process, and I'll give you a reference to a resource that is available from CWNP that can go a little bit deeper into some of that if you want to. Then we have, of course, the new WPA3 Enterprise requirement of PMF. So other than that, WPA3 Enterprise without 192-bit mode still looks an awful lot like WPA2 Enterprise. WPA3 Enterprise 192, though, does require certain things to come up to compliance with certain requirements of some governments and other organizations, where we end up using GCMP 256 or AES 256 GCM, it's sometimes called. We use SHA 384, ECDH P384, ECDSA P384, or we could use RSA greater than 3072. All right, so what's all this mean, given that you don't see a 192 in any of those? So we got all these different things that we have to use, but none of them say 192. They all say higher numbers. So AES says 256. ECDH, ECDSA, SHA, they all say 384. RSA says 3072. So where's the 192 in here? Well, the answer is that SHA 384 has an equivalent bit strength of 192 bits. So it's about the strength of the encryption solution. And RSA, to get to 192 level bit strength, you've got to use 3072-bit RSA keys. So it's all about what is required to get to that equivalent bit strength. It's a bit of a simplification, but it's a way to think about it to help you understand why it's called WPA3 Enterprise 192. Now, if you want to go into more details on it, well, then we have this thing called the Commercial National Security Algorithm, CNSA suite, which is defined by NIST and is required by some government agencies within the US, for example. And it's going to define certain requirements that ultimately, in the end, force you to use EAP-TLS. And this is why we generally say WPA3 Enterprise 192 requires EAP-TLS, because it's easier to simply say that than to get into all the details, particularly if you're talking to a manager, of why you end up saying we have to use EAP-TLS, okay? So EAP-TLS becomes the effective requirement because that's what's going to give us the capability to implement all of the different parts and pieces that are required to get WPA3 Enterprise 192-bit. Now, once again, this WPA3 transition mode is there, but I want to point out that it may not be a best solution for any real-world implementation. It might be better to just use different SSIDs. So one SSID for your WPA3 users and another for your WPA2 users. So at least that way, you're not affecting any potential vulnerabilities on your WPA3 users because of your WPA2 users directly. Here's the issue. The issue is that a WPA3 client could be pushed down to WPA2, even though it could use WPA3 with certain attack methods and issues within these networks. And so the better solution may be to use separate SSIDs to resolve that issue in many cases. Now, there is a thing that is made available through the Wi-Fi Alliance that can help. That is that if a client detects that an SSID supports WPA3, it will flag that SSID to never downgrade to WPA2 in the future. But it's not really implemented consistently or at all by many vendors. And it can even break clients because of the way the clients try to implement it. So, and I'll talk a bit more about that in just a second. But the key thing is with transition mode, the AP is broadcasting a beacon frame that advertises multiple AKMs. And so the client will use the one that it can support. Now, to take this a bit further, one of the resources I wanted to point out to you that is available to you is within the digital edition study guide for the CWSP 208, as well as in the CWSP 208 e-learning. You have a section on simulators and learning tools, they're called. This is one of the things we do. If you've not noticed recently in the last, I don't know, year and a half or so, we've started releasing some digital editions of our study guides. And the reason for that is we asked you, the community, would you prefer this, particularly if you get extra things with it? And significantly, nearly all of you said, yeah. And so basically you get the PDF of the book, and then you get these simulators and learning tools. And then further down, there are these resources that are available. These can be white papers, important blogs, things like that, as well as YouTube videos related to each chapter of the book. But these learning tools and simulators are just that. Some of them are simulators, simulating certain things. So for example, one of the things people get confused about with security a lot of times is the concept of coverage. And so they think, okay, here's my building, this external box here. This is my building. And hey, as long as the hacker is outside of the building, right, then they shouldn't be able to access my network. But you can see, even if my AP is all the way over on the other side of the building, that hacker still has, it looks like, a signal strength of minus 86 dBm. It's weak, but it has that signal strength. But notice all he has to do is use a semi-directional antenna and improve it by 6 dB. If that semi-directional antenna has 5 dB of gain, now he's up to neg 77. So the whole point of this is to show what the coverage looks like to the client. That's the whole point of this simulator. So you can move the client around now. So obviously, if I move the client up here to this corner and I aim its semi-directional antenna, see how the coverage is changing dynamically. Obviously, the AP's actual coverage is not changing. This is the perspective of the hacker and what the coverage looks like to that hacker now, since it's using a directional antenna. And we can even go all the way up to a Yagi antenna, really get some good directionality. Okay, so this is just an example of one of the simulators that helps you to conceptualize and understand these concepts as we are evaluating these things. Now, one in particular down here is the WPA3 SAE learning module. This is a learning module. Now, when you see learning module or learning tool, that means that it's going to take you possibly deeper or explain in different ways some of the concepts that are introduced in the certification. And so here we see the discussion of inherent infrastructure risk with the older versions of security and Wi-Fi. What is forward secrecy? How does that work? And if we go over here to threat mitigation, you'll notice there's this transition disable. So this is a bit that can be set according to WPA3 specifications in order to tell a device, hey, once you detect it on WPA3, don't ever try to connect with WPA2 on that SSID anymore. But the reality is that you do not get that in most environments. So for example, the host APD implementation, if you don't know, That's the default supplicant in Linux distributions. So that implementation does implement it, but that doesn't mean that everything's going to implement it. It may not be supported by all of the vendors' systems, all the clients properly, and there's not really wide support for it yet. So it's something to think about for the future, but it's not something you can say and trust is there today. And then, of course, we go further, and over here you get the details of GCMP. So, for example, a lot of people aren't even aware of this, but 802.11be made some changes to this, and with EHT, the PHY specified in 802.11be, GCMP 256 support is mandated. Now, be careful about wording. GCMP 256 support is mandated for any EHT RSNA stations. All right, what's all that fancy stuff with all those acronyms mean? It means any device that implements 802.11be according to the standard will have support for GCMP 256. Notice it doesn't say GCMP 256 use is mandated. It says support is mandated. So that's important when it comes to understanding what's going to actually be implemented. Now, MLO, multi-link operation, part of 11be, is that the Wi-Fi Alliance has said GCMP 256 is mandated for MLO. So if we're using MLO, we need to use that. Now, why is that? It's because GCMP is more efficient than CCMP when you're dealing with high throughput. And so it gives you the ability to implement it effectively with the higher throughput of these. So again, the terminology is important. And this is why, for example, there were some studies done where they looked, seems like it was in New York City. It may not have been. I forget the exact area where they did this survey, but they went around and they captured the networks that were running Wi-Fi 7, and they said, all right, how many of these networks are actually using GCMP 256? And one out of hundreds or many was actually using it. The others, obviously it's supported, but it's not what they were using. So just because something is mandated to be supported doesn't mean it's mandated to be used. And that comes only over time with clients supporting it and so forth. Again, this learning module is just part of the complete, what we're actually looking at it here live. This is what the CWSP 208 digital edition of the study guide looks like, which is available for purchase through the website. So again, it gets you the PDF of the study guide for CWSP, and then all of these different simulators and learning tools, and then the curated resources that are available for enhanced learning beyond just what the content within the book itself. And that gives you an overview of what's going on in Wi-Fi security up to date now to 2026.